Are we alone in the universe? For most of human history, we had no way of answering it. The stars appeared as tiny points of light, impossibly far away, hiding whatever worlds might orbit them. But today, thanks to powerful telescopes and decades of scientific discoveries, we know something astonishing. Our solar system is not unique. In fact, our galaxy alone is believed to contain hundreds of billions of planets. Many of them orbit stars remarkably similar to our Sun, and some may have conditions that are surprisingly close to those on Earth. The question is no longer whether planets outside our solar system exist. The real question has become, could life exist on any of them? Today, we'll explore how life emerged on Earth, what makes a planet habitable, how scientists discovered distant worlds, the 5 most promising candidates for life beyond our solar system, and the incredible missions that may finally answer one of humanity's oldest questions. Earth didn't become home to life by chance alone. It is the result of an extraordinary combination of conditions that developed over billions of years. The first essential ingredient is liquid water. Water acts as an excellent solvent, allowing complex chemical reactions to occur. Every known form of life on Earth depends on it. The second requirement is a stable source of energy. Our Sun provides a nearly constant flow of light and heat that has remained relatively stable for billions of years. Without that stability, complex life might never have had enough time to evolve. Earth also possesses a thick atmosphere. It traps enough heat to keep temperatures suitable for liquid water, while shielding the surface from harmful radiation and helping regulate the planet's climate. Another critical factor is Earth's magnetic field. Generated by the movement of molten iron deep inside the planet, it deflects much of the charged radiation coming from the Sun. Without this invisible shield, the solar wind could gradually strip away the atmosphere, just as scientists believe happened on Mars. Our planet also benefits from active plate tectonics. As continents slowly drift across the surface, carbon is continuously recycled between the atmosphere, oceans, and rocks. This natural thermostat helps stabilize Earth's climate over geological timescales. Even Earth's unusually large moon has played an important role. It stabilizes the tilt of Earth's axis, reducing extreme climate fluctuations and creating more stable conditions for life to develop. Finally, Earth contains all the essential chemical building blocks of life: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Combined over billions of years, these ingredients eventually produced the first simple organisms, which gradually evolved into the incredible diversity of life we see today. One of the most important concepts in astronomy is the habitable zone, often called the Goldilocks zone. This is the region around a star where temperatures allow liquid water to exist on a planet's surface. If a planet orbits too close to its star, and temperatures become so high that water evaporates, potentially triggering a runaway greenhouse effect like the one that transformed Venus into a scorching world with surface temperatures above 460 degrees Celsius. If a planet is too far away, water freezes solid, creating an icy landscape similar to Mars or the frozen moons of the outer solar system. Earth happens to orbit almost perfectly within the Sun's habitable zone. What if our planet were just a little closer to the Sun? Average temperatures would rise dramatically. More water would evaporate, increasing atmospheric water vapor, a powerful greenhouse gas, which would trap even more heat. Eventually, Earth's oceans could disappear entirely, but what if Earth were slightly farther away? The planet would cool. Ice sheets would spread toward the equator, reflecting more sunlight back into space and causing temperatures to fall even further. This positive feedback could eventually freeze nearly the entire planet. Simply existing inside the habitable zone doesn't guarantee life. A planet must also have an atmosphere, sufficient mass, long-term climate stability, and many other favorable conditions. Still, the habitable zone gives astronomers the best place to begin their search. Finding planets around distant stars is surprisingly difficult. Planets produce almost no light of their own, while their stars are often billions of times brighter. Instead of looking directly at the planets, astronomers usually detect their effects on their stars. The most successful technique is called the transit method. When a planet passes in front of its star, it blocks a tiny fraction of the star's light. Sensitive telescopes measure these tiny, repeating dips in brightness. From this, scientists can calculate the planet's size and orbital period. Another widely used technique is the radial velocity method. Planets don't simply orbit stars, both objects actually orbit their common center of mass. As a result, the star gently moves back and forth. This motion slightly changes the wavelength of the star's light through the Doppler effect, allowing astronomers to estimate a planet's mass. In rare cases, telescopes can even capture a planet directly using advanced instruments that block the overwhelming glare of its star. This method, known as direct imaging, works mainly for very large planets orbiting far from their stars. Another fascinating technique is gravitational microlensing. According to Einstein's theory of general relativity, massive objects bend light. When one star passes in front of another, its gravity acts like a natural lens. If a planet orbits the foreground star, it creates an additional distortion in the light, revealing its presence. Together, these methods have revolutionized our understanding of the universe. The search for habitable worlds truly accelerated with NASA's Kepler Space Telescope, launched in 2009. Kepler monitored more than 150,000 stars simultaneously and confirmed thousands of new exoplanets, proving that planets are common throughout our galaxy. After Kepler, NASA launched Tess, the transiting exoplanet survey satellite. Instead of observing a small region of the sky, Tess scans almost the entire sky, searching for planets orbiting nearby stars that are easier to study. The European Space Agency's Gaia mission has measured the positions and motions of more than 1 billion stars with extraordinary precision, improving estimates of planetary systems throughout the Milky Way. Today, the James Webb Space Telescope has taken the search one step further. Rather than simply finding planets, Webb can analyze the chemical composition of some planetary atmospheres by studying starlight passing through them during transits. Scientists have already detected molecules such as water vapor, carbon dioxide, methane, and carbon monoxide in several exoplanet atmospheres. These discoveries represent an important step toward identifying possible biosignatures in the future. Although thousands of exoplanets have been discovered, only a handful currently stand out as especially intriguing. Only 4.2 light-years away, Proxima Centauri b is the closest known potentially habitable exoplanet to Earth. It orbits the nearest star to our solar system and has a mass similar to Earth's. However, its star is a red dwarf that frequently produces powerful stellar flares. These eruptions could strip away the planet's atmosphere, making conditions for life extremely challenging. The TRAPPIST-1 system contains 7 Earth-sized planets, with several located inside the star's habitable zone. Among them, TRAPPIST-1e is considered one of the best candidates. It has nearly the same size and density as Earth, and may possess a rocky surface with liquid water, if it has retained a suitable atmosphere. The system has become one of the primary targets for observations by the James Webb Space Telescope. Located about 49 light-years away, LHS-1140b is a rocky super-Earth orbiting within its star's habitable zone. Its relatively calm red dwarf star emits less intense radiation than many similar stars, making long-term atmospheric stability more likely. Recent studies even suggest that if an atmosphere exists, the planet could potentially support a global ocean or large regions of liquid water. K2-18b has attracted enormous scientific attention. It is significantly larger than Earth and orbits within the habitable zone of a red dwarf star. Observations with the James Webb Space Telescope have detected methane and carbon dioxide in its atmosphere. Some researchers have also reported tentative evidence for dimethyl sulfide, a molecule produced on Earth primarily by marine microorganisms. However, this possible detection remains highly uncertain and has not been confirmed. At present, there is no evidence that life exists on K2-18b, but it remains one of the most exciting planets for future atmospheric studies. Discovered by the Kepler mission, Kepler 442b is often considered one of the most Earth-like planets ever found. It receives roughly 2/3 of the sunlight Earth receives from the Sun, placing it comfortably within its star's habitable zone. Although it is about 1/3 larger than Earth, computer models suggest it could maintain stable surface temperatures suitable for liquid water if it possesses an atmosphere. The search for life is only beginning. NASA's Nancy Grace Roman Space Telescope will help discover thousands of additional exoplanets using both microlensing and direct imaging technologies. The European Space Agency's Plato mission, expected to launch later this decade, will search specifically for Earth-sized planets orbiting Sun-like stars. Meanwhile, the Extremely Large Telescope, currently under construction in Chile, will possess a mirror nearly 39 meters across, allowing astronomers to study exoplanet atmospheres with unprecedented detail from the ground. Looking even further ahead, NASA is developing the concept of the Habitable Worlds Observatory, a future space telescope specifically designed to directly image Earth-like planets and search their atmospheres for oxygen, ozone, methane, and other possible biosignatures. These missions may eventually detect convincing evidence that biological activity exists beyond Earth. Just 30 years ago, humanity didn't know whether a single planet existed outside our solar system. Today, we know of thousands. We've discovered rocky worlds, ocean candidates, planets with complex atmospheres, and entire planetary systems unlike anything in our own neighborhood. Yet despite all these discoveries, we still have no confirmed evidence that life exists anywhere beyond Earth. Perhaps life is incredibly rare. Or perhaps the galaxy is filled with living worlds waiting to be found. Every new telescope brings us closer to the answer. Maybe the first unmistakable sign of extraterrestrial life won't come from a spaceship or a radio signal. It may arrive as a faint chemical fingerprint hidden in the atmosphere of a tiny planet orbiting a distant star. And when that day finally comes, it won't just change astronomy, it will change humanity forever.